invitation. Is nice to see everyone. This, even through the small screen of the computer. I hope we can see each other in person soon. So this is a joint work with Wanderson Lima from Brazil and Franco Vargas Palet from the US. And so I'm going to talk about several things. I mean, the things that we did. Some things are related to a global description of the mean curvature flow. I'm going to define all the things soon, but I just want to give you a big picture idea of what we did. So some things are about the mean curvature flow in generality, things that work for all dimensions, and there's other things that we did that are just an application of some of these observations for two-dimensional surfaces evolving in three manifolds, specifically in manifolds with negative curvature, and some specific applications will be for hyperbolic three manifolds. So I will spend some time trying to describe the main ideas, and then perhaps at the end I'll comment on some of the proofs. But please feel free to interrupt me anytime. So I know maybe there's several people that might have some specific questions, so I'm always encouraging you to interrupt me anytime. Okay, so let me start by reminding people what is the mean curvature. So the mean curvature is going to be important because everything we do is related to the mean curvature. So one quick way to define the curvature, if you remember the curves of curves and surfaces when you were on the undergrad, for a surface in R3, at any point of the surface, we can, you can find the intersection of the surface with some plane that contains the normal to that surface at that point. So let's say this is the plane, and that gives you a curve. And then, of course, you can talk about the curvature of this curve. And then, it's part of the theory that there are two directions that are called principal directions. These are two orthogonal directions that correspond to the maximum and the minimum curvatures of all the directions on the surface. And then the average of these two directions is what we call the mean curvature. And we can think of this mean curvature as a vector. And this is a normal vector, which is defined regardless of the orientation that your surface might have. Okay, so in this picture, I just erased the normal vector that I did above, because actually the mean curvature vector will point downwards because the curve is curved that way. The surface is curved that way. Okay, so this is the mean curvature, and then we denote it by h of p, mean curvature vector. So the mean curvature vector is related to the area and to variational problems of the area because of the following formula. So we're going to denote, the area of a surface as just the area of S, and then you can, if you have your surface S, and you have some normal vector field V, it's perhaps bigger here, smaller here, and so on. You can perform variations of this surface in the direction of these vector fields, perhaps something like this, and then you can take the derivative of the area along these variations for time 0, and then this will give you a number. So I'm going to denote that this is an operator, which is the first derivative of the area, so that's why I'm putting this delta there, of S in the direction of V. Okay, and this is a number, and the point here is that it is related to the mean curvature because this is the integral of the product of the mean curvature vector times v ds with a minus. Okay, so yeah, so this is what we call the first variation formula for the area, and then but there's two observations that I would like to draw from here. The first is perhaps a definition. The definition is the critical points of the area. These are called minimal surfaces. So S is a minimal surface or minimal hypersurface. So by the way, all the drawings that I'm doing are for dimension 3, but this idea of the mean curvature vector, is generalized in the obvious way to hypersurfaces of any ambient manifold. You can always do this local construction of finding the directions of the operator and computing the mean curvature vector as a trace of the derivative of the normal vector. So we say that S is a minimal hypersurface if it is a critical point of the area. And by that, let me write that, if it is a critical point of area, and this means that the derivative of the area of S in the direction of any vector field is 0. So this is a normal vector field. Okay. So, and of course, because of the integral above, you'll see that this is the same as asking that the mean curvature vector of the surface is 0 for all points in the surface or hypersurface. Okay, so notice that a minimal surface is not necessarily a minimizer. So this is something perhaps a little bit unfortunate, that minimal is not necessarily a minimizer. But the right way of thinking of this is about a critical point. I'll show you some examples soon. But before that, I'm going to talk about what the mean curvature flow is. So if we think that this area functional somehow lives on the space, is a function on the space of hypersurfaces, then you can imagine that this will have some sort of gradient flow or negative gradient flow, and this is what the mean curvature flow is. So you see that because of this formula here, the mean curvature vector gives you the fastest direction in which you can decrease the area of a surface. So the mean curvature flow is, let me just put it here between parentheses, is the negative gradient flow of area. So the mean curvature flow starts with a surface. So let's say that is a surface in a manifold. So you can think of a hypersurface in an ambient manifold dimension n. And then the mean curvature flow is a function of time, is a one-parameter family of these inclusions, if you like, that at time 0 is the identity. So it just gives you the surface that you start with. So perhaps if this is your S, then the mean curvature vector does something like this here. Here is 0, and then it goes this way on this side of the surface. And then for positive time, what we ask is that the derivative of this function coincides with the mean curvature vector. Okay, so the surface is evolving by the mean curvature flow. So perhaps in this drawing right here, what will happen is that for some positive time, you'll have something like this. Right, so this would be your ST for T positive. Okay. So yeah, So some examples of this mean curvature flow that are perhaps easy to understand are the sphere. So if you have the round sphere Sn in R, or Sn minus 1 in Rn, then the mean curvature vector is constant, and the sphere actually evolves by shrinking to a point. Okay, so what happens is that after finite time, it collapses. So some people will say collapses, vanishes, or extinguishes. So these are all similar terms. What it means is that the flow disappears or wants to disappear, and this is a problem because your definition started with a differential equation, and then when you have the singularities forming, then your differential equation doesn't have a meaning anymore, at least in classical terms. So because of this, you have to find alternative ways or weak ways of talking about the flow, so that you can take into account singularities that occur naturally. So you want your evolution to don't care about the singularities sometimes and go along or do some tricks in order to pass through singularities. So I'll discuss several ways in which people do this. The other example I can mention is a dumbbell. So this is an example that you'll see very commonly referred to in the literature. So this is like two spheres connected by a neck. And then what happens here is that after some time, so this is example 1, example 2. After some time, your evolution became disconnected, and perhaps there's a singularity there. And then after that, you have two spheres now that are evolving independently. Okay, so this is just another type of singularities that might occur. So another example is a cylinder. In the case of a cylinder, you're going to see again the mean curvature vector points inwards for each circle that is, say, one of the fibers, and then this whole figure evolves towards a line, and it also disappears in finite time. And then finally, I wanted to mention the torus. If you have a torus that is perhaps very thin, I don't know if I can draw a torus that is very thin, so something like this. Right, so very thin torus. These will evolve into kind of circle, right? Just the circle that is at the center of the torus. So these are just examples of evolutions that have singularities, and you see these are not the worst type of surfaces you can consider. We're talking about the sphere, a torus, a cylinder, etc. And even these simple examples develop singularities in finite time. Let me give you now examples of both things together: minimal surfaces and mean curvature flow. So the idea that I have in mind here is that we can think of the typical picture of a Morse function, where you have the gradient flow of the Morse function, and then you have some critical points. So when you evolve along this flow, you might end up at critical points of your function. So what I'm saying is, let's say this is the graph of a function. We have something like this, perhaps. So this is the graph of a function from R2 to R. And if I take a point, let's say here, the gradient flow of these might take me all the way to this point here, which is a stable point. It's a local minimizer. And then if I take this point here, it might take me to this other stable point. It's a different one. And then this point here is a saddle point or a local maximum that is, it doesn't move by the gradient flow. Okay, so how will this look in the case of surfaces? So this is for a function from R2 to R. Okay, so this is the gradient flow. So what you think really is that this point was down here and you evolve it to this point here, and this point was right here and you evolve it to this point here, etc. So so one drawing that I'd like to do, let me see if I can accomplish this. Is to show you different behaviors that can occur, kind of like to illustrate some of the points that will become relevant later. Okay, so here what I'm imagining is I have a cylinder. In my cylinder, with this metric that I've drawn, I'm gonna draw now some minimal geodesics, but think of these as surfaces, please, or hypersurfaces. So the geodesics, by the way, geodesics are the one-dimensional equivalent of minimal surfaces, right? A geodesic minimizes length, a minimal surface minimizes the area locally. So yeah, here I want to draw, it's not a cylinder anymore, I have some topology there, and then perhaps I can find some other geodesics here. And then here is a very special one that I will talk about very soon. So so notice something. This surface here, it's a local minimizer, and when this happens, we also refer to this as a stable surface. I'm going to define that in a minute. But these are also local minimizers. These two local minimizers are, when you consider them together as one surface, they are in the same homology class as this surface, but one of them by itself is not. That's just something to have in mind. And then we can understand this in terms of its variational characteristics infinitesimally. So we say that a surface is stable, or S is stable, if now I'm going to look at the second derivative of the area of S in the direction of a vector field V, and if this is greater or equal than 0, we say that S is stable. Here, by the way, I'm assuming that S is minimal. So it's already a critical point. I'm just classifying the critical points by the index of the second derivative, if you like. So this is equivalent to looking at the Hessian of the function here and saying, okay, a local minimizer has Hessian that has all the eigenvalues greater or equal than 0 because it's a local minimizer. Other critical points are different. And then we say that S is unstable otherwise. Okay, so in the picture, this is stable because it's a local minimizer. These ones here are stable. This could be also stable, but let's say that is unstable, just for the sake of it. But it could be unstable in the same way the function, I don't know, x minus x4 is stable. So, if you have the function minus x to the 4, the second derivative there is going to be 0. So technically speaking, it's stable. But, in general, something that looks like this with, general metrics, generic metrics, is going to be unstable. And then this particular one here is stable. So this is like the function x cubed, right? So the function x cubed, again, has this saddle point here, whose second derivative is 0. So this is what we'll call stable degenerate, meaning that the first eigenvalue of the second derivative is actually 0. Okay, So these are just some examples of minimal surfaces, how I think about them. And then the way the mean curvature flow relates to this picture is for example, if I have an unstable surface, you can see very quickly just from the equation of a minimal surface from the second derivative, that if you push it in the normal direction using the first eigenfunction, I don't want to get too technical, but there's a way of pushing the surface. Let me just erase this. There is a way of pushing your surface a little bit forward, let's say in this direction, so that now this has become what we call mean convex. So a surface S is mean convex. Now it doesn't have to be minimal, of course, it's mean convex. Or more generally, we will say has non-vanishing mean curvature. I think this is an awful color. Sorry, let me change that. So it has no vanishing mean curvature if H P is never zero, is different than zero for all P in S. Okay, so there is a way of pushing forward an unstable surface to produce something that is mean convex to the outside of the surface, and then what the mean curvature flow will do, at least in for small times, is evolve these towards that direction, of course. So you will obtain something like this, and then what you will expect, at least in this picture, is that this converges, keeps evolving by the flow and converges towards this stable surface. So pretty much in the same way that here we had this unstable point on top that evolved toward this stable surface here, a stable point here. So this is what is happening in spirit. You can do the same thing towards the other side. You can also produce a mean convex surface towards the other side of your unstable surface. But in this case, you see the picture is suggesting that something might happen. There's probably going to be some singularity along the way, and something like this. And you could either have a geodesic there or a minimal surface. Sorry, a geodesic, at least in the picture that I'm drawing it. You can imagine that there's a geodesic there that is singular. But with surfaces, this doesn't happen. And in fact, what will happen in a case like this is that it will split, and you will end up having two evolutions, each one converging to something stable and smooth. So this was proved by Brian White. So I will mention this later on. Okay, and then so again, this is also a convergence towards something stable, but you see something is happening with the topology of your surface. Okay, so because of the needs of dealing with singularities of the flow, we have these weak notions of mean curvature flow. And there's several of them. This actually took me a while to understand the difference between them, but I'm going to be talking mainly about two of them. One is called the level set flow. And the level set flow, some people call it the set theoretical solution, or the maximal set theoretical solution of the mean curvature flow. I'll talk a little bit about that later. The point here is that things evolve, and they might stop being smooth, and that's fine. The flow, because it has this set theoretical spirit, it will keep evolving until it either vanishes or converges to something at time infinity. And then the other approach is the mean curvature flow with surgery. So I believe this was first done by Husken and Sinestrati for the dimension greater than 3, and then at the same time, more or less at the same time, by Hasselhoff and Kleiner in dimension 2, and Brendel and Huskin also in dimension 2. And in this type of flow, what happens is, so let me just draw an example. I have my notes here. So let me just describe what happens. So you can imagine that you have some surface S0 here, S0. So let me call it S0. And that is converging to some S infinity stable surface. And then along the flow, some singularity wants to develop, something like this. So perhaps one way of drawing this would be, I don't know, perhaps it looks like this here, and a little bit more like this. And then after, it continues in this way. But then at the moment the singularity develops, you have perhaps something like this. So that's not a good drawing, sorry. Something like this. And then after that, this went to a point and this continues. So something like that. So the levels of flow will do this. The levels of flow will show you all these pictures, and we'll keep moving forward. Another thing that the levels of flow can do is that it might happen that all of a sudden it thickens out. So one typical example is the evolution of this figure after some time, some positive time, looks like, perhaps like this and like this. Oops. It thickens out. It develops some interior. So that might happen on the levels of flow. With the mean curvature flow with surgery, what people do is that the picture is very similar. Oops. The picture is very similar, but instead of waiting for the singularity to occur, when you reach this stage, what happens is that if you have some control about how singularity occur, and people do this in some cases, then you might actually perform a surgery here that will produce two new surfaces or two new pieces, each one that can be evolved by the mean curvature flow a little bit more after the singularity time. So in the surgery, what will happen is that people will find some time where you can cut here, and now you have these two surfaces. Let me just use perhaps the yellow color here to illustrate. So this is one surface, is this one. I just put a cap there, and this is the other one, right? So now I have a sphere and then some other surface, and they're both evolving now by the mean curvature flow, and it continues nicely, and it kind of imitates what the levels of flow does after a certain time. Okay. So these are the two notions that we consider. We consider these when the levels of flow, when the dimension for any dimension, well, between 3 and 7, and then the mean curvature flow with surgery, we only consider it for dimension 3, but we believe that we do can also be can be done for the mean curvature flow with surgery in higher dimensions as well. Okay, so we just didn't went through it because we were interested in application for three-dimensional manifolds. Okay, so let me now start asking some questions that will motivate the theorems that we prove. So, but before then, are there any questions? Does anybody have any question? Okay, so the question, perhaps one first question. So this is for dimension 3, between 3 and 7. So what happens with the mean curvature flow if S is non-separating. So let me tell you what do I mean by that. So non-separating means that M minus S is connected. So, one picture illustrating this will be something like perhaps some sort of torus that is, something like a genus 2 surface times S1, so something like genus 2 surface times S1. And then the question is, if I take a surface like this and I evolve it by the mean curvature flow, with, for example, using the level set flow notion, what happens with this evolution? And then one answer was given by Ilmanen. Ilmanen showed that the evolution of S exists for all time. This means that it doesn't vanish in finite time. Okay. So he showed this with generality, but you can ask more questions. For example, okay, fine, it doesn't vanish in finite time, but for example, can it somehow spin around indefinitely? Around this torus? Can you see the surface giving many loops? Does it converge to something nicely or not? And then what our first result is answering this. So let me just write down theorem. In the case that we have non-vanishing mean curvature, so if H of P is non-zero for all P in S, then as T, the evolution, the level set flow of S converges to S infinity, where S infinity is a smooth, stable minimal surface, minimal hypersurface, and the convergence is smooth. So what might happen with multiplicity? Let me explain what this means. So so the remark, before I explain what this means, let me just remark what was known before and stress the fact that our contributions are not on the regularity of these phenomena. So this was actually proved by Brian White, regularity for S separating and mean convex was proven by Brian White. And the regularity theory that we use is his theory. And in that case, in the case of Brian White, the multiplicity can happen with, it can be at most 2. So what does this mean? This means that when you see your S infinity surface, then your ST might be converging something like this. This is the worst that can happen. You have 2 fronts converging towards the same stable surface. So this is multiplicity 2. That's what I mean, multiplicity 2. So this is no longer true. This is no longer true for for non-separating surfaces. This is not true in general. And then we produce an example for this. So it's not so hard to produce an example with arbitrary multiplicity after you see this. I'm just going to show you one with multiplicity 3. So the example would be, I hope I can draw it, something like this. So this is your surface, and then you have some sort of sphere connected with a neck to the surface, and then you can have, because it's non-separating, you can send a neck around the manifold so that it comes back here. So actually, let me draw a little thicker here so that it corresponds. And then you put this neck also around the same sphere. And then you can keep doing this, right? So you can produce a third neck. Let me draw it in purple. This third neck comes now towards the second neck and then enters into the first neck as well. And then you have, this figure that I hope is easy to understand. But what will happen is just that a little bit after you run the flow, all the necks are going to cut quickly, and then you're going to end up with S and then 3 concentrical spheres. So, for example, if it happens that inside of these 3 spheres there is a minimal sphere, then the flow will make these 3 concentrical spheres that have mean curvature pointing inwards converge to that minimal sphere inside. So there you have a flow that the flow it has the property that is mean convex, right? So the mean curvature of the surface that I constructed here is non-vanishing. So the mean curvature vector points always towards a certain direction, and it's never 0. But the convergence is with multiplicity greater than 2. And then you can imagine that you can keep doing this game of putting necks and making the neck inside of the other and so on to produce examples with higher multiplicity. So yeah, that's the first thing we did. So yeah, this in particular, this says that so the hypersurface, the evolution of the hypersurface doesn't vanish in finite time, but also kind of spin around indefinitely. It will converge to some minimal surface. So I'll talk about the proof about that, the proof of this fact a little bit later. So let me just mention what we did in dimension 2, for example. So you can now that you know that things converge, you can start asking questions, more specific questions for some situations. So in dimension 3, let me just remind you of the work of Mick Simon Yao. So remember the classical work of Mick's where they're trying to find given an isotopy class of surfaces, they're trying to take one's surface in that isotopy class and then deform it into minimal surface on that class. So the question is, can we do the same thing with using the mean curvature flow? Can we do something similar? So let me just make a drawing again. So I'm thinking some situation like this. So again, I have something like a genus 2 surface time S1, if you like. So now here, I'm going to put some little bump on my metric. So now, and then I'm going to make a surface something like this. It goes around here and comes back. So in the theory of Mick Simon Yao, what will happen for the surface, let's say this is an incompressible surface. Incompressible means that the P1 of the surface is injective into the ambient manifold. What you can do, you can isotope this all the way to here, because you can go around this sphere without any trouble by an isotopy and deform it towards the stable minimal surface. But now, if you're using the mean curvature flow to do this, then now you care about this bump here, so you cannot avoid seeing a minimal surface there. So perhaps using the mean curvature flow, what you will obtain is something like this surface here, and again this one here. Okay, so this should remind you a little bit of what Meek-Simon-Yau do, but it's slightly different. And of course, it might be that there's also some stable minimal surface here, which is not a minimizer, and then in that case, this is what the mean curvature flow will see, and not the minimizer. Okay, so somehow the theorem gives you something similar to what Meek-Simon-Yau does for incompressible surfaces, but it's different. So let me just write down the theorem that we proved. So the theorem says that, so take S, now is S2 in M3, and we're assuming that S2 has non-vanishing mean curvature. The reason we're asking for non-vanishing mean curvature is to use the regularity theory of Brian White. That's it. So, but anything that, if you have a flow for which you already know that you have some regularity theory, the global analysis we do is the same. Okay, so what happens in this case, so if S is incompressible, then S infinity, the limit of the flow, can be decomposed into two parts, two sets of connected components. One connected component, S prime, is incompressible, and the other is a union of spheres. So this is two-dimensional minimal spheres, or RP2. So remember that S infinity is minimum, right? This is what we proved in the previous theorem. And the convergence is smooth. And then what happens here is that regarding the incompressible component on the limit, if S prime has either multiplicity 1, in which case S prime is diffeomorphic to the original surface S, or S prime occurs with multiplicity 2, in which case actually the surface double covers the limit. Okay, so think of for example a sphere converging to RP2 inside of RP3. Okay, so what happens here is that S prime is one-sided, and S is isotopic to a tubular neighborhood of that. Okay, and then another question one might ask is, okay, well, we have these spheres here that don't let us make this continuous isotopy towards the stable minimal surface just using the flow, but when can I do that? And then one of the reasons is the following question. So when can we isotope? I don't think this is a good use of the word. When can we deform by isotopies that decrease the area, that always decrease the area? And this is, of course, having in mind, for example, applications in combination with Minmax theory, in order to construct sweep outs, as we actually do. This is This is useful. So this was one of the questions we had in mind. So you see, in this example that I draw here, it's very unlikely that you can do that because of this bump here. This bump will ask you to go beyond the area that you originally had in order to pass around it and converge toward this stable surface. But you see, the problem only appears with these the components that are not incompressible, which are S2 or RP2, and these cannot happen in negative curvature. The theorem that we prove is the following. So imagine that as above, we have S incompressible and M3 has, again, non-vanishing mean curvature for regularity reasons. And M3 has negative curvature. Negative sectional curvature. So for example, a hyperbolic manifold. So then, in this case, S prime prime is empty. Okay, so because there cannot be minimal spheres or RP2 in a negatively curved manifold by Gauss-Bonnet in the Gauss equation. And then in this case, there is a monotone isotopy from S towards S infinity, the stable surface, such that the mean curvature is also non-zero along the isotopy. So of course, at the last time, the mean curvature is going to be zero, but in between is not. Okay. So let me now. Any questions? So this isotopy will decrease the area. So let me just explain. One application of this is the following theorem that we prove in combination with Minmax theory. So if M3 is a hyperbolic manifold, which is either Quasifusion, I'm going to explain what that means, or fibers over S1, with fiber surface of genus greater or equal than 2, which is the only thing that can happen, by the way. I mean, but I'm just stressing this out. And then Quasifusion means, topologically, it will be S cross R. So think of, in this case, we have a manifold that looks something like this. And in this case, we have something like this. Then in these two scenarios, then M3 admits a foliation whose leaves are either minimal or have non-vanishing mean curvature. So and the way to prove these is, so let me talk about a little bit about the proof of these, just because I think I'm running out of time. So is that when you have a cylinder, something like this, you can find some stable surfaces on your cylinder that are disjoint. You, for example, can find one on, in this case, you can find one just by applying mixed Simon-Yaos, if you like. Or in this case, it's easier. You can just, that Quasifusion manifolds at infinity, they have, convex surfaces, the mean curvature pointing inwards. In fact, from Karenbach and Ralph Maceo, they proved that each Quasifusion manifold, they have a unique CNC foliation at the ends at infinity. So you can begin with this and then use the flow to find some stable minimal surfaces inside. And then in that case, you're gonna find two stable surfaces inside that are what we call their outermost, meaning that every other minimal surface lies in between these two stable ones that belong to the fiber. And then once you chop your manifold using these stable surfaces on the fiber, you can do in between each one of those a min-max. So you do a min-max, again, on the isotropy class of the fiber. This is the min-max that is known as Simon-Smith. It was generalized to situations like this by Marquez and Neves in the work on the rigidity of min-max spheres. And it has been used recently by Lyubomic and Ketover and Antoine Song. And then what the idea is that after you do this min-max, you obtain these unstable surfaces, and then you can use the mean curvature flow to produce a foliation from the stable ones, from the unstable ones towards the stable ones. And then in that way you have a foliation that is a non-vanishing mean curvature of minimal leaves. So the reason we were interested in this is because of the Quasifusion manifold. So let me just finish by mentioning what we do in this case, with just drawing. So Quasifusion manifolds, what people used to describe them, the way people used to describe them is, well, you have these ends that they're foliated by CMC, by the work of Picard and Maceo. But then in the middle, you don't know exactly what happens. What we're saying is, well, you can do a little better. You can say that there's two stable surfaces in these Quasifusion manifolds, and then in between, you can find this joint family of stable surfaces, and then these index 1 surfaces in between that you can use to produce a foliation. So this is the way we're completing this picture for Quasifusion manifolds. And then one thing about Quasifusion manifolds is that they have a deformation theory. And in fact, what we're going to call this, just for the sake of this talk, a Quasifusion end. So these are Quasifusion ends. So manifolds that are hyperbolic manifolds that are called convex compact. That means that the convex core, I'm not going to define that, but there's a region in the manifold that's convex that essentially looks like the whole manifold. So you have some big ends. So these are hyperbolic manifolds with finite area. And then in the middle, you have some topology. And these ends, they're all like something like this, surfaces of genus, cylinders of surfaces of genus greater or equal than 2. And then, we're calling these Quasifusion ends. So every time one of these Quasifusion ends is incompressible, you can find an outermost surface for that particular end using the mean curvature flow in the way we did. And then if you know a little bit of hyperbolic manifolds, when you have finite volume hyperbolic manifolds, these are very rigid. This is mass law rigidity. But when you have infinite volume, then you have a rich deformation theory, actually. So for each conformal class that you pick at each of the infinite of these ends, you're going to have a hyperbolic metric inside. So the other thing we did was to study the continuity of the outermost stable surface with respect to variations of these parametrization of hyperbolic metrics. And we show that the surface, this stable surface, is upper semi-continuous in different ways. But for almost every of these hyperbolic metrics, these are stable minimal surfaces, and the deformation is continuous. Did I already pass the time, or do I still have more time? Could someone tell me, please? Hello,
I think it's
Isabel,
okay.
are you?
You spend 5 more minutes. So
5 more
don't worry.
minutes. Great, great. So let me talk about this. Let me mention something that that I think is interesting, which is, the Quasifusion manifolds. They were studied by Karen Uhlenbeck in the 80s, early 80s, and specifically one subset of Quasifusion manifolds, which is called almost Fuchsian. These are manifolds that look like this, but they only have one minimal surface inside, one stable minimal surface. There's no other minimal surface. And then the point is that she proposed, to study the set of formal solutions to the minimal surface equation in a hyperbolic manifold, and try to find analogies between the set of hyperbolic metrics and the space of formal minimal surfaces. The reason is that both have the same dimension. So if the genus of the surface is G, the dimension of the matrix is 12G minus 12. These are space of metrics, has this dimension, but also the space of formal minimal surfaces. These are solutions to the Gauss-Codazzi equation for a minimal surface in a hyperbolic dimension. And using those spaces that she studied, we were able to understand a little bit about the discontinuities of the map of the outermost minimal surface. And what we found is that sometimes this outermost minimal surface is degenerate stable, and the Quasifusion manifold in that case will look like this. It's a little bit weird, but it happens. And then what's interesting about this, to me at least, is that, hyperbolic metrics, these are analytic metrics. Sometimes you might think that certain degeneracies cannot occur, but they actually occur. And then what we found is that the outermost can be sometimes like this, some sort of saddle point like x3, x cubed. So this is a degenerate outermost. So yeah, I think perhaps I can also mention what is the idea for the flow. So because it's easy to understand, the idea is that you can cut your manifold around your surface, and then you can glue it back with copies of itself and somehow produce. So let's say that there was a topology here inside, just for the sake of the picture. So you're going to have copies of your manifold and copies of your surface. And then the topological fact, just from covering space theory, is that when you minimize in a non-trivial homology class the area, you obtain a non-separating surface. That's the first fact. This is because if it was separating, then you can erase one of these components that was separating. So you can always assume that the minimizer in the homology class is non-separating. And then whenever you have two non-separating surfaces within the same ambient manifold, you can do the same idea. These are of course oriented, so you can cut along them and glue them with copies of each other using the orientation to construct this cylinder. It turns out, this is just by Poincare duality, that the covering space that you obtain is the same one. This is the covering space towards this torus here. So when you take a minimizing surface, you can actually lift it here and produce minimal barriers. So now you have the surface that you want to evolve, which is a compact surface, is going to lie between two of these minimal barriers. So all the theory that was developed for separating surfaces in compact regions applies to non-separated surfaces this way. And then because now you have to figure out that why the projection behaves well with respect to this the mean curvature flow. So and the reason is because the mean curvature flow has the non-avoiding principle, or sometimes also the inclusion principle is called, which is going to tell you that the evolutions of all these copies of the same surface is going to remain disjoint for all time, and because of that, they project well towards the cylinder, the original cylinder. So, and then you have to do, some local analysis and make sure that whenever you perform surgeries, these surgeries lie within the regions where you have a diffeomorphism, and so on. But this is the main idea of why you can use the regularity for the separating case to the non-separated case. Okay, and I think I should stop here. Thank you.
Okay, thank you, Marco, very much.